Okay, in this video, we're going to continue to look at functions and some other properties of functions, most of which I think you have met before in Algebra 2. A few may be new to you, but they're fairly intuitive. So let's get started. Let's first take a look at this function. F of x is this rational function here. We say rational because there's this fraction bar making a ratio. When we have a rational function with variables in the denominator, we run into a little bit of a problem, particularly with domain. So can you tell me which x value would not be in the domain? That's right. You would have to say that 3 is not in the domain because if x were 3, the denominator is 0 and division by 0 is undefined. So 3 is not in the domain. All other real numbers are in the domain except for 3. And we know how to write that in interval notation. It would be two distinct intervals uh, from negative infinity to 3, not including the 3, and then from 3 to positive infinity, not including the 3, and it's the union of those two sets. Well, based on yesterday's notes, that may have been pretty obvious to you that 3 was not in the domain, but what does that look like when we try to graph this function? I'm not going to go into great detail about graphing the function, but I do want to know, what does this produce? Uh, what would it do to the graph of the function? Well, I've got a setup here with a way to maybe plot a few points of this function, and maybe that'll help us describe what happens to the graph. Let's pick a few points around x equal 3. Maybe let's start with x equals 0. If x were 0, 3 minus 0 is 3. 3 plus 0 is 3. We have 3 divided by 3, or 1. So when x is 0, y is 1. 0, 1's on the graph. Pick 1. I'll get 4 over 2, which is 2. So 1 comma 2 is on the graph. 3, undefined. Can't use it. How about 4? 3 plus 4 is 7. 3 minus 4 is negative 1. 7 over negative 1 is negative 7. So 4, negative 7's on the graph. Oh, about there. Let's pick 5. 3 and 5 is 8. 3 minus 5 is negative 2. 8 divided by negative 2 is negative 4. So 5, negative 4 is on the graph. Roughly there. We'll do one more. How about 6? 3 plus 6 is 9. 3 minus 6 is negative 3. 9 divided by negative 3 is negative 3. 6, negative 3 is on the graph. Oh, roughly there. Well, that may be enough points to maybe see what's going on. Do you have a better idea of what's going to happen to this graph now? Maybe from Algebra 2. At x equal 3, we have what is known as an asymptote, a vertical asymptote. It turns out that any element where the domain is restricted, a single element like 3, produces a vertical asymptote. And so the graph of this rational function would look very close to what I've got drawn here, showing a vertical asymptote. The values would approach 3 from the left and from the right, but never reach it. Now let's use our imagination a minute and imagine what would happen, out there close to positive infinity. What if we let x be a billion or a trillion or something really, really big? We'd have some giant number in the numerator, a billion or a trillion and 3, divided by roughly a negative billion or trillion. So a positive trillion divided by a negative trillion or close to it would be very close to what? Very close to negative 1. And what would this, in this case, negative 1 produce on the graph? Pause video and let's see. If you answered a horizontal asymptote, you'd be correct. That is the value of the function. the value of the function, what f of x would approach, uh, but never quite reach, is a horizontal asymptote. We saw that we let x be a big number like a trillion. This function would be a trillion divided by negative a trillion, give or take a few, which would produce a -1. So a horizontal asymptote at -1. There are three simple rules to help you determine if a function has a horizontal asymptote, and if it does, where is it? Um, so first you expand into any factored form of the numerator and denominator and get it in expanded form. Each polynomial is in expanded form, and determine the highest degree term in both the numerator and denominator. If the degree of the numerator and denominator are the same, like it was for f of x up here, then the asymptote is the line y equal whatever, the ratio of the coefficients of that dominant term. Uh, Here, the coefficient of the highest degree term, which is 1, the coefficient is a 1. Here, the highest degree term is also 1, so they have the same degree. The coefficient is 1. The ratio of those coefficients, 1 over -1. So the line y equal -1 was the horizontal asymptote. Now, if the degree of the denominator, the highest degree term of the denominator, is greater than the numerator, then the horizontal asymptote will be at the line y equal 0, or the x-axis. And if the degree of the numerator is greater than the degree of the denominator, then we really don't have a rational function that can actually be divided, and we'll see that later in the course. So there is no horizontal asymptote. So have a look at this new expression for f of x and determine where the horizontal asymptote would occur if there is one. And pause the video and respond. Well, let's take a look at the degree of the numerator and the degree of the denominator. The degree of the numerator, the highest degree term, is a square. Its coefficient is 1. And the degree of the denominator, is the highest degree term a square? No, this is in factored form. If you distribute this x, the denominator would be x to the third power minus 2x. And the highest degree term is a cubic with a coefficient of 1. So since this is a case of number 2, the degree of the denominator is 3, the degree of the numerator is 2, the denominator's degree is greater than the numerator, so the asymptote would be the x-axis, or the line y equal 0. Okay, I'd like you to put those two concepts together. Find any vertical or horizontal asymptote of the function described by this rational function. And then give me the vertical asymptote, if any, and horizontal asymptotes, if any. Well, the vertical asymptote is going to be what makes that denominator 0. So let's just set that expression equal to 0 and solve it. X squared equal 4. The square root of both sides, we get x equal plus or minus 2. So we have a vertical asymptote at +2 and one at -2. Two vertical asymptotes. For horizontal asymptotes, we look at the degree of the numerator and the degree of the denominator. The degree of the numerator, the greatest term is a square, so it's degree 2. The denominator, the greatest degree is a 2 as well, so they have the same degree. So we just look at the coefficients of the square terms. That's a coefficient of 1, and it would be y equal the line y equal 3 or 1. That would be 1, 2, 3, a horizontal asymptote there. That's enough for us right now. I will show you how to graph this, what the rest of it's going, what else is going on with this thing in another couple of weeks. Another thing we could talk about, or a feature of functions, is whether or not, or on what intervals they increase or decrease. Now, the words are what you think they mean. There's nothing special here. A function is increasing if its graph rises from left to right as we read a graph. It's decreasing if its graph is falling as we move left to right. If this is the graph of a function, f of x, can we determine over which intervals the function is increasing? Well, you can clearly see that this part of the graph, if I go left to right, even though it's got a downward arrow here, as I move from left to right, it is climbing. So, it's also climbing, I guess, from this point in the graph to about that point in the graph. So how do we express those intervals over which it's increasing? Well, let's see. This interval is from negative infinity to the point -6, and that's the interval over which it's increasing. At -6, it looks like it's flat. And this is from -3, which is a turning point, so it's not included, and it runs all the way up to +2. And those are the two intervals where the function is increasing. Can you examine the graph and tell me where the function is decreasing? I hope you mentioned that the graph is decreasing over this interval, these two intervals here. I'm getting better with writing with a mouse, I think. I'm working on a alternative though. Decreasing over these intervals. Wherever a function changes from increasing to decreasing, it forms a little hump, or from decreasing to increasing, it forms a little valley. These are called extrema. That's an extrema of the function. It's a maxima, or singular would be maximum, where it makes a hump, and it's a minimum wherever it makes a valley. Functions may have both local and absolute extrema. A local extrema are the humps or valleys, maxima and minima. But does either of these functions have an absolute minimum or maximum? Well, I don't think so. And I know so because these arrowheads that we see tell us that this function continues going infinitely downward. It will never bottom out and have an absolute minimum. And it will continue climbing infinitely upward and never have an absolute maximum value. But can you think of a function that you know of and have worked with that does have either an absolute minimum or maximum? Well, the one I had in mind for you was the ubiquitous parabola. I know you studied that at length last year in Algebra 2, and we're going to have another whack at it this year as well. I'd like you to take a look at this graph, this function, and tell me if you think that these two areas of the graph represent local extrema, and to answer whether or not the function itself has an absolute extrema. Well, I hope it wasn't a trick question. We have to examine really closely what's going on right here. I've got a tool to help maybe amplify that right there. If we look closely, does it look like the graph is changing from an increasing to decreasing? I would say it does not. It's increasing and it sort of flattens out, not an extrema. And here we're increasing maybe slightly and then increasing more. So it never does change to decreasing. There were no extrema in that region. As far as absolute extrema, well, sure, just like the parabola, this area right here is a absolute minimum because the graph is never going below that. Another feature of functions that we'll address is whether or not a function's graph represents or has any symmetry. As you can see in these pictures here, we see symmetry in this case, the first one around the y-axis. If I folded the graph right along the y-axis, the right side would fold right on top of the left side. And we say that those functions are even. The test for whether or not a function is even is if I plug -x in for x and simplify, and I get the same expression as I started with. The second case, we have x-axis symmetry. Once again, if you fold this along the x-axis, the top would fall directly right onto the bottom. But it is worth noting that this one, if it has x-axis symmetry, it's not a function. This is going to fail the vertical line test. And origin symmetry would be if I did both folds. Fold the x-axis, then fold the y-axis, and we would end up right on top of ourselves. Now, the test algebraically for whether or not a function has origin symmetry, which is also called an odd function, is to plug in negative x for x and evaluate the function and simplify. And if we get the opposite of the original function f, then the function is odd. And we'll take a look at a few examples. Okay, I'd like you to have a go at it. Determine whether this example, the square root of x squared plus 2, is even, odd, or neither. Another way of asking, does it have y-axis symmetry or origin symmetry? Pause and give it a try. Well, I hope you plugged in negative x for x like I did here, and simplified. Negative x squared is x squared, equivalent, and found that f of x and f of negative x are indeed equal, so this function is even and has y-axis symmetry. One more example. Pause video and determine if number 2, if f of x is even, odd, or neither. And I hope you found that when you plugged in negative x for x and did that little bit of simplifying, it doesn't matter where I put the negative sign in that regard. So we have the original function f of x, excuse me, f of negative x does equal, f of negative x does equal the opposite of the original function. So in this case, we say it is odd. And that's all I have for you today. So I'll see you tomorrow ready to work the exercises.